Hello and welcome in Engineering Materials and Metallurgy subject. I am Professor A.P. Godke, Assistant Professor in Department of Mechanical Engineering of S&D College of Engineering, Yeola. So today we will discuss about the topic or unit number 4, that is the heat treatment of the steels. So heat treatment is the process, or it is the treatment where we can apply the heat to the metals into the surface, into the furnace, and the properties of the metals are going to change. So basically steels are formed by the combination of carbon and ferrous. So for specific application, we require the certain properties inside the material. So to improve the mechanical properties, thermal properties, and other properties of the steel, the heat treatment process is carried out at a particular temperature, and cooling is performed in a particular environmental condition or cooling media. So such treatment is called as a heat treatment to improve the properties of the steel. So cooling curves of a pure iron. So in this diagram, you can see the cooling curve for the pure iron. So the source of this is a VD Kodgiri reference book. So here you can observe this the various phases of the pure iron at with respect to the temperature and time, that is cooling time. So on x-axis there will be the time, that is a cooling time, starting from 0 to increased time, and on y-axis there will be the temperature, that is the melting temperature of the metal or the phase change temperature for the steel, starting from the 0 to 1539. So for pure iron, 1539 is the melting point. So above this melting point, the pure iron present into the liquid phase. So here at this point, the pure iron present in the liquid phase, then as the temperature decreases from this temperature to 1539 degrees Celsius, for somewhat time, that is a soaking time, we can consider it as our cooling time, the temperature remains constant and there will be no change in the phase. After that, once with respect to time, temperature decreases from 1539 degrees Celsius to 1400 degrees Celsius. The phase change from liquid changes to the delta iron phase, which has a body centered cubic structure. So here phase is a delta iron. Then for a particular period of time, temperature again constant. So there will be no phase change. The phase remains as a delta iron. After that, again temperature decreases from 1400 degrees Celsius to 910 degrees Celsius. So in this stage, the time will be slightly increased and the phase of the iron is a gamma iron and the structure is a phase centered cubic close pad. After that, for some time, the temperature remains constant, that will be the 910 degrees Celsius. Then phase change does not change. After that, temperature decreases from 910 degrees Celsius to 768 degrees Celsius with respect to some change in the time. So the phase change occurs from alpha iron, gamma iron into the alpha iron, which is non-magnetic in nature and body centered cubic close packed is the structure. After that, for 768 degrees Celsius constant temperature for some period of the time, the phase change does not occur. After that, from 768 degrees Celsius to room temperature, the phase changes from alpha iron to again alpha iron. So here phase change does not occur in this temperature range, but the non-magnetic nature gets converted into the magnetic nature, and structure remains same, that is body centered close packed structure. So in this diagram, what we learn how the pure iron gets formed from liquid state to solid state. So the different phases are liquid, delta iron, gamma iron, alpha iron, and alpha iron with the magnetic properties. Second is the iron carbon equilibrium diagram, which is there applicable for the steel and cast iron. So here different types of phases are existing this type of so this diagram represent the percentage of carbon present in the steel and cast iron. So here on x-axis you will observe the percentage of carbon starting from 0 to 6.67, and on y-axis you will observe the temperature in degree Celsius. So depending on the cooling and the percentage of composition of the carbon into the iron, the different phases are existing for the material, and different reactions you can see here for first region. For this region also one reaction is there. For this region another reaction is there. Then depending on the percentage of carbon and temperature, different phases existing into the diagram. So this diagram is called as a iron carbon equilibrium diagram. So here this phase is a liquid phase, this phase is a delta phase, this phase is a gamma phase, this phase is the austenite, then this phase is a alpha ferrite, then this is a gamma plus Fe3C. So Fe3C is the cementite phase, then here it is alpha plus cementite, here gamma plus liquid, here gamma plus delta, here liquid plus delta, here ladiburite plus Fe3C. Then here a reaction is a eutectic reaction, here a reaction is a peritectic reaction, here the reaction is a eutectic reaction. So at 0.8% of carbon and temperature, eutectic reaction occurs. So here at 0.8% the reaction occurs is a eutectoid reaction. At 4.3% of carbon, the reaction is a eutectic reaction. So at 2% carbon, there will be the steel. From 0.008 to 2%, there will be the diagram for represent for the steel. And from 2% to 6.67%, this diagram will be there for the cast iron. So we'll get the different types of cast iron depending on the variation of the percentage of the carbon into the iron, and we'll get the different types of the steels by varying the percentage of carbon from 0.08 to 2%. So the percentage of carbon by weight is there on the x-axis, and on y-axis there will be the temperature. So depending on the change in temperature, the phase change occurs with respect to the composition of the material, and desired properties are achieved into the steel or cast iron. Next, this is the iron carbon equilibrium diagram from the basis of the heat treatment. So here gamma is the austenite phase, alpha, here it's alpha, alpha is the ferrite phase, here delta is the delta iron phase, then Cm is the, here Cm is there, ACM or Cm is the cementite, which is a Fe3C. So this is the cementite. Then depending on the percentage of carbon, so this region from 0% to 2%, that will be called as a steel, and from 2% to 6.67%, that will be cast iron. Then in steel there are two types again, hypoeutectic steel and hypereutectoid steel. Then here also hypoeutectic cast iron and hypereutectic cast iron is there. Then here a liquid phase is there, here delta ferrite or delta iron phase is there, here alpha ferrite phase is there, here percentage of carbon is 0.025, here carbon percentage is 0.08%. This is the ACM line. Here the phase is a delta plus liquid. Here phase is a delta plus austenite. This region is a austenite. Then this region is a austenite plus liquid, that is austenite in liquid. Here ladyburite and not ladyburite. Here it is a liquid and cementite. Then this is a liquid phase. Then this is a austenite and cementite, that is called as a ladyburite. So it is austenitic ladyburite and cementite. Then this is austenite to perlite transformation. Then cementite and ladyburite region is this. Then this region is a perlite and ferrite. Then this region is a perlite and cementite. This region is a cementite, perlite and transformed ladyburite. Then magnetic change of cementite occurs at this temperature, that is a 210 degrees Celsius. So here temperature in degree Celsius and here temperature in degree Fahrenheit. Then different phases existing in the iron-iron diagrams are as follows. So first phase is alpha ferrite. So it is the interstitial solid solution of carbon in BCC alpha iron at low temperatures. So solubility of carbon in alpha iron at room temperature is 0.08% and increase with the increase in the temperature to about 0.025% at 727 degrees Celsius. So this phase is soft and ductile in nature. So this is the first phase, alpha ferrite. So this is the phase where alpha ferrite is there, and carbon ranges from 0.08 to 0.0082 to 0.00 not 0.0082 to 0.025. So this phase is called as a alpha ferrite, starting from the temperature 210 to 727 degree Celsius. So here temperature will be 727 degree Celsius. Next is austenite. So it is the interstitial solid solution of carbon in FCC gamma iron. Phase is stable above 727 degrees Celsius. Then the solubility of carbon in gamma iron at 1147 degrees Celsius is 2%. It is soft, ductile, malleable and non-magnetic phase. So here in diagram you can observe that this region, so it is stable at 1147 degrees Celsius. So in this temperature range, it will be stable. So here at 2% of carbon, the gamma iron phases exist. Next is the delta ferrite. It is an interstitial solid solution of carbon in BCC delta iron at high temperature. Similar to alpha ferrite except occurrence at high temperature. So this is the phase which is a delta ferrite, or it is also delta iron. Next is the cementite. It is the interstitial compound with the fixed composition of 6.67% of carbon. So here at 6.67% phase exists is a cementite. It is a orthorhombic structure and extremely hard and brittle in nature. So this is all about the cooling curve for the pure iron. Then iron carbon equilibrium diagram for steel and cast iron. Then with respect to the heat treatment and different phases existing in the iron carbon equilibrium diagram. Thank you for watching.